All right, so today we're going to continue on what we've been working on this entire time, which is binary trees. But now we're going to introduce even more structure, and we kind of hinted at it before, where we're actually going to store stuff in this data structure so that we can have fast retrieval, fast insertion, and fast deletion, right? The three basic operations. And for that, we've already hinted at it. They're binary search trees. Generally, again, we store data into each tree node, and we're going to store it in an ordered manner here, so that everything will have a key element, k, right? Now, if you've got a key element k in your tree, then every node in the left subtree it will have a key value less than it, the left side tree, and then every node in the right subtree will have a key value greater than it. And that way you can pretty easily see how you could search through this tree by saying, okay, well, here's my key element. I found what I'm looking for. Otherwise, what I'm looking for is less, so I traverse left. What I'm looking for is greater. I can traverse greater. Right now, here's a general depiction of this. That if I've got a key element here, everything in this left subtree is less than that key element k. Right? Everything in the right subtree is going to be greater than k. Now that's an inductive property, so that holds for every node, not just the root node, but every node in the entire tree. Here's one such tree, but we're only considering integers, okay? Now you can verify that for each one of these nodes, 50. Is everything over here in its left subtree less than 50? Yep. Is everything over here greater than 50? And again, like I said, it's inductive. So let's go ahead and take a look at this node here, 20. Everything in its left subtree is less than 20. Everything in its right subtree is greater than 20. This is the same structure that we were using for our other large tree. It's just that I've now put in key values here. Okay. All right. Is this tree full? Is every node present? Nope. The left subtree hanging off of 60 is not, for example. There is no left child of 45, etc. Right? So that may or may not be a problem in the final analysis. We'll keep that in mind. But now let's think about the basic operation of, say, searching through this tree. Right? How would you go about searching for, say, 42? Right. Oh, let's go with something easier. How about 49? So you would start where? At the root, like you would start at everything, right? Is that what we're looking for? No. So is there any need to go down to the right side of the tree at all with, like, say, a full pre-order or post-order traversal? No. Why? Because we know that everything over here is greater than 50. Therefore, 49 would not be over there. Okay? That sounds really familiar. What kind of other algorithms acted like that? B-search, right? Binary search. Except that with binary search, what was the major requirement? That it be sorted, of course, but also that it be stored in an array. Because in order to jump to the middle element, we have to have random access. We have to be able to jump to the ith element for free and then check, is that the thing I'm looking for, or do I search in the left half or the right half? We get the same potential benefit here of being able to jump to the middle because of the tree structure right here. If roughly half the tree is in the left part and roughly half the tree is in the right part, then by nature of the structure itself, we're starting in the middle. And we can use a divide and conquer strategy to go left or go right, cutting it in half each and every single time, potentially giving us that order log n behavior similar to binary search. Right? So let's go ahead and complete this. I know I don't need to go left, so I'll go, or I know I don't need to go right, so I'll go left. Now, is 40 the thing I'm searching for? Nope. The thing I'm searching for is larger, so which way do I go now? To 45. Right. 45 is not the thing that I'm searching for, so which way do I go now? Down to the right, and guess what? I'm done. I found what I'm looking for. There were only 4 comparisons in that case. What if we were searching for, say, 50? So here's the key, and here's the number of comparisons, comps. Right? What if we were searching for 50? Guess what? We got lucky, right? How many comparisons did we need to make sure that it was there already? 1. Right? We could get unlucky, though. We could say search for, say, 13. Oops. Let's go with 13 here. How would you go about searching for 13? Start at 50, no to go left. 40, go left. 20, go left. Right? 10, go right. 15, go left. 12, go where? Right into nowhere, resulting in an unsuccessful search. With an unsuccessful search for binary search, of course, we could return a negative index value. We could throw an exception. We could return null. We could do whatever we wanted. That's all an implementation detail. But how many comparisons did I need to make to determine this? 1, 2, 3, 4, 5, 6. Right? 6 comparisons there. Is there any other search that will result in more comparisons than that? No. Why? Why did I choose that? That was the deepest possible node, meaning that all of these search criteria, any search that I perform is going to be order what? Order D, where D is the depth of the tree. Now, if we go all the way back to the beginning when we introduced trees, I gave a justification for why we wanted to look at binary trees. Because if they were full, there was a guarantee on the depth, that the depth was going to be logarithmic. All right? Now, if we have that guarantee, then guess what? Order D is going to end up being order log n. Do we have that guarantee, though? No, because this certainly isn't even full, right? In fact, we could have a very, very skewed tree, remember? Right? It's called a linked list. In which case, order D becomes order n, and we're right back at square one. We won't worry about that just yet, though. Okay? All right, so that's how you can search a tree. How would you end up, say, inserting a new element? Well, if it were an empty tree, right? Here's my empty tree right now. This is a corner case, and I wanted to insert, say, I don't know, 20. How would you go about doing it with an empty tree? Just make a new node, and there's your new root, right? Now suppose that I've inserted, I'm somewhere, and I'm over here. Now I've got this tree. 20 is, oh, by the way, 20 is already in there. What if we wanted to insert 20 here? Insert 20, ... Should we allow that or not? It's already there. So are we going to allow duplicates? Okay, that's a design decision. Let's not allow duplicates. What if we did allow duplicates? What does our general structure look like now? You just got to be consistent. Is it breaking ties to the left or breaking ties to the right, but not both, right? Because if you did both, right, which way do I go, right? It could be that way, it could be that way, right? So you can allow duplicates, you just have to be careful here. In general, though, ultimately we're going to implement this using a comparator. Comparators should impose a total order and not a poset, a partially ordered set, right? You've seen that in, say, 235, right? You have a set and you've got a partial order on it. Maybe? Okay, hopefully. All right, so let's just jump into it and let's go ahead and insert something else. That 13, it was not in there, right? So let's go ahead and put it in there. Could I put it over here somewhere? Oh, there's a spot. Right? Can I just put it in the most convenient, shallowest spot to keep the tree as full as possible? No, that would violate the binary search tree property. Okay. So I definitely need to go over here somewhere. Oh, okay. Can I go off of 45? Again, no. Where's the only place that I could put this? As where I would have found it had I found it, right? Where? As the right child of 12. How did you know that? We already went through that operation, right? We went through a search to find, oh, it's not there. But if it had been there, if it had existed, there's where it would be. Well, now we're inserting it. So we need to make it exist by putting it right there. Okay? In other words, insertion involves searching through the tree, finding that it's not there, and then inserting it. Guess what? That means that we're always going to do this as a leaf. Are you ever going to insert it, say, in between here? Probably not. I mean, you could do that, and you'd have a lot more work to ensure that the binary search tree property still held, but ultimately we're always going to insert as a leaf. Okay? Those are the first two operations that I just wanted to give you a heads up of how they work. Let's go ahead and talk about an actual implementation. And then we'll go ahead and implement those as we're going along. And then eventually we'll go ahead and talk about how to delete things. Okay? So let's go ahead and implement a binary search tree. I'm going to start from scratch here. I'll call it binary search tree. Right. There we go. I'm going to go ahead and start from scratch here because you could go ahead and put this into an inheritance hierarchy, right? What is a binary search tree? It is a binary tree with more structure. So maybe that's a subclass of the binary tree that we already did. Extends binary tree. Maybe. Right? Maybe you don't want to do that for the same reason that that we didn't want to subclass a sorted list from a list. Do you remember that? Right? A sorted list is a list, right? But then it inherits all of its methods, including add this element to an arbitrary location. Does that sound like a sorted list to you? No. We don't necessarily have that same problem depending on our design of our binary tree, which I forget. I don't even think we added any add methods. I just gave you this big giant tree and then we did all the other algorithms on it. But in any case, I want to start fresh here. Okay. Now, what is our tree going to hold? What is our binary search tree going to hold? Stuff, right? If I say stuff, what is that yelling out to you? Parameterize it. We'll come back to that, okay? For now, our stuff will be integers so that we can make sense of it, okay? And that means we need a root. So private, what is it, tree node? Tree node. We can reuse the same tree node, but we'll go ahead and force it to become an integer tree node, root. This is a binary search tree for integers and integers only for now, okay? Let's go ahead and create a constructor here, public binary, well, actually, binary tree, binary search tree, excuse me. This dot root is equal to null. What else might I want to keep track of? Maybe a size? Okay, private int size equals 0. And so if I insert something, I will increment that. If I want to remove something, I'll decrement that, right? Searching would have no effect on the size. So this dot size is equal to 0. Okay, there we go. All right, well, in order to search for something, I need to make sure that something is in there already. So I propose that as our first operation that we have an add method, right? So public void, say, because we're not going to return anything, add element. And what is our element going to be? It's going to be an integer x. Okay. Add to the left. Add to the right. Do either of those sound right? Nope. Add as a leaf. A leaf? What's a leaf? I know what a leaf is because it's a binary search tree, but you don't tell me what to do. That's my stuff, right? I am the binary search tree. All right? Don't tell me how to add stuff. I'll add it. Right? Okay. So help me out. What was our first corner case? The root. So how do I detect whether or not this tree is empty? If this root is null, or if the size is 0, either way. Right? This is a special corner case. I create a new tree node, right? Tree node integer. And I set this dot root equal to it. New tree node integer. And x will be inside that tree node. Is that it? Size plus plus. Then move on. I'm done, right? So what should I have done inside that if condition? Return, you're done, right? There we go. Okay. Otherwise, we know that the root is not null. And so we have a picture that looks maybe something like this. Right? So what do we need to do? We need to find it first, right? We need to find this guy right here. But if this guy doesn't exist, then are we going to find it? No. What do we actually need to find? We need to find this guy in order to put it over here. In other words, if 13 existed, what would we need to find? Its parent. Okay? So, I propose that sounds like another operation. Maybe we put that into a different function so that we can use it. Right? So, for example, public tree node t find parent of, say, x, integer x. There's the value x. Okay? And then what the expectation here, integer. The expectation here is that if x doesn't exist, if x exists, then we'll go ahead and return its parent. Otherwise, if it doesn't exist, like that's where it should be, we'll still return its potential parent. Okay? I would put that into the documentation, but I wouldn't call it potential parent. Right? All right. Does it seem like that should be public? No. What is it returning? A tree node, right? If you want to, you can go ahead and have a public method to get or element exists. All right, Boolean element exists or contains, say, contains x or something like that, integer x. Right? That makes sense because you're telling the outside world, yeah, you're talking about integers, and this is a binary search. This is a collection that holds integers, right? But exposing a tree node to the outside world, oh yeah, here you go. Here's a tree node. That allows them to muck with the parent, the left child, the right child. All right? So I'm going to go ahead and make that into a private method instead. Okay? For now, I'm going to return null. I'm going to think, gee, that's a nice thing to have. I'll give that to myself later on, and I'll make sure that there's a to-do here, implement. Right? If I had that, how could I use it up here in add? Tree node of integers, p is equal to find parent of, say, x. Right? Once I've got that parent, what do I need to do? Let's take a look at a general case here. Right? So here's the parent, or here, it's an actual node, p here, parent. Right? Now I want to insert this new key node that I'm going to create. Where do I insert it? Do I insert it down here, or do I insert it over here? When do I insert it over here? If k is less than the parent. When do I insert it over here? When k is greater than the parent. So all I need to do is have an if-else condition here, right? There's the parent. If x is less than p.getItem, then I will insert to the left, ... Right? Else, if p.getItem, the parent is greater than that, or sorry, the x is greater than that, then I'll go ahead and insert to the right, ... Now, did I need that if condition right there? Not if I'm not going to allow duplicates, right? If you want to allow duplicates, then there you go, and it's just an else condition now. Right? I'll go ahead and leave it like this, and I will get rid of that. Right? Or, I mean, I guess you could say the else. If we're really not going to allow duplicates, we could throw an exception here or just immediately return. Right? If I immediately return, then this is no op, right? No operation. Or I could throw an exception or could do whatever I want. Right? Okay, I'll go ahead and leave it like this. How do we insert to the left? Well, first of all, in either case, I would be creating a new tree node, right? Tree node integer child is equal to new tree node containing x. There we go. And that new child will be the left child of the left, so p.set left child to be the child. Otherwise, we insert it to the right, p.set right child to be the child. Now, is that the only relationship that I probably want to maintain? So let's take a look at our tree node again. It has a left child, a right child, and a parent. So conceptually, P is the parent, but I didn't set that. So child dot set parent to be P. In fact, at this point, I'm regretting calling it P. Let's go ahead and rename it. Refactor, rename, parent. Right, there we go. And child dot set parent to be parent. Now, repeated code, repeated code. It's going to happen no matter what. So what should we do? Put it right there. All right, do something like that. Now, arguably, it's not always going to happen. What if it's a duplicate? Then we would not have set that up. Okay, fine. It's whether or not you're allowing duplicates and what you do in that situation. Right. I'll go ahead and keep it like this. There we go. All right. Now, is it going to work? Probably not, because I haven't done that thing right there. But let's set ourselves up in the demo right here. Okay. So it's not a binary tree anymore. It's a binary search tree. But I lost my ability to make it into strings. Right? It's no longer parameterized here. And it's called a BSD. Right? Equals new binary search tree. And there we go. And I want to really add that element bst.add 20. There we go. Okay. Well, that's going to work. Why? Because that's my corner case. There's 20. Let's see if it will work if I have, say, 30 and then 10. Why did I go in that order? 20? Where will 30 go? To the right, and 10 will go to the left. I'm making sure that it works there. Okay. I set myself up for that test. Of course, it's still not going to work because we still need to do this thing right here. Right. Now, find parent. Okay. Help me implement this now. How would it work on this one example? Where would I start? At the root. All right, so let's do that. All right. So I will have a tree node, t, integer, right? And I'll call it current. And where do I start it? At this root. Okay. So here's my current. Where do I go next? I am searching for, say, 13. I look at the current's key, and if the key is less than the current, where do I go? Go left, right? Otherwise, if it is greater than the current, where do I go? Go right. Right? Dot, 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 until what? Until, yeah, when will I stop? Right there, right? When current falls off the end. Or it is, what's the other condition here? Strictly less than, strictly greater. What's another condition? K ends up being equal to the current. In which case, I found what I'm looking for. Say that I was searching for 12 instead of 13. I would end up returning its parent instead. Okay. So let's codify that a little bit. What kind of a loop would you suggest here? A while loop. While loop. Why not a for loop instead? Yeah, you don't know up front how deep you're going to go into this tree, right? While some condition. Okay. If the key value x is less than the current dot get item, then I will traverse left. Else, if the current dot get item is less than x, I will traverse right. Else, now the only other condition here is that the current is equal to x. Okay. And if that's the case, I found what I'm looking for. What should we return? Currents, say what? Parent, right? Because I'm finding the parent, right? Okay. And do I need to break out of this while loop? No. Just, you found what you're looking for. Stop. Just like binary search, right? Did we worry about breaking out of the loop in binary search and then returning something? No. Stop. Just return. Right? Okay. Traverse left. How do I traverse left? I will update my current to be current dot get left child, right? Otherwise, I traverse right. Current is equal to current dot get right child. There we go. Now, what's my while condition here? When you've fallen off the edge of the tree, right? There's where 13 should be. I want to return 12 though, right? So how do I know that my current here, current has fallen off the tree? Current is null. While it's not equal to null, keep going, right? Okay, can I return current dot get parent here? Just like I did here. Current starts at the root. We would have broken out of this while loop when it's null though, right? Okay. Back to the whiteboard. What we want is this guy. Oops. What we want. Sorry. That's not the undo. That's the undo. What we want is this guy right here. Right? So suggestions. If this is the current, then what's the parent? Let's do another variable. Prev for previous. Let's keep track of two things. Okay? Let's keep track of the current and the previous. And all coders everywhere wish that these were both the same number of letters so that everything would line up. And that's why we go ahead and say cur and prev. Right? Because now everything does line up. Right? I will go ahead and keep it full words here though. In fact, there's a word for that. There's a word for the casing where, okay, fine, you don't have the same number of characters in your variable names. We'll go ahead and align the equals signs here anyway. There's a term for that, but I forget what it is off the top of my head. Does anybody know? No? Okay. All right. Anyway. So why do I start the previous at the null? Because if I start at the root, what is my previous? I came from nowhere. So my previous is null. Right? Now, if I'm going to update the current, what should I do before I traverse left? Previous is equal to current. Right? In fact, I could do that right here because I'm going to do that here as well. Right? And it really doesn't matter that if I do it here or not, but you're doing it in all three of these cases. There we go. Previous. Right? And then I go either left or right. Okay? That means I can return previous. Right? It's as simple as that, I think. Right? Let's find out. So, demo, I'll run it. No exceptions. Did it work? Yeah, I have no idea if it worked. What's one way that we could check to see if this works? I could go ahead and run the debugger and see. Let's see. System.out.println. Hello. Set a breakpoint there and run my debugger. There we go. And there's my BST. Right? There's its root. The root's item is 20. Okay. The left child's item is 10. The right child's item is 30. Just like I expected. And what about its parent? Its parent is some tree node. We never did the toString method there. So expand that out though, and its parent should be, guess before I click it, 20, right? And likewise, the parent of the left child should be, oops, where? Now I've lost the forest for the trees here. The left child's parent should be 20. There we go. Yep. In fact, guess what? Expanding this out is a hierarchy. Guess what that is? It's a tree, right? All right, well, that was kind of a sophisticated way of doing it. What's a less sophisticated way that I could have done it? Let's think about this tree. What if I built this tree and it all looks good now? I could have done a tree traversal, like a pre-order, post-order, or in-order traversal on this. Just for some reason, I'm feeling like, let's do an in-order traversal of this, right? As practice. In-order traversals are going to be what? Left, root, right. All right? So what's the first thing we do? Well, we don't do 50 because we need to do the left subtree first. We don't do 40. We do the left subtree first. We don't do 20. We don't do 10. We don't do 2. We do the left subtree first, which is empty. And then we do 2. And then we do the right subtree, which is empty. Okay. We come back up here. I've done the entire left subtree of 10, so I do now 10. And then I do the right subtree. 15 and 12. But do I do 15 immediately? Nope. I do 12, then 15, and then nothing. Hopefully you start to see a pattern here. Without even thinking about it. What's the next value? 20, 24, 25. What else? 40, 45, 48, 49, 50, 60, 75, 80, 85, 90, 95. How was I able to determine that? This was called a what kind of order again? An in-order traversal. Why do you think we call it an in-order traversal? Because when it's done on a binary search tree, guess what it does? It gives you the order of all the elements. So, let's go back and steal the code from the binary tree to do an in-order traversal. Where is it? BFS, in-order traversal. I'm going to steal you. There we go. And put you into this binary search tree implementation. Hey, did I have to change anything? Yeah, because before it was just T's. So should I make it more terrible and make it a list of integers, or should I make this implementation better? Let's make this implementation better. How can we make it better? By making it not about integers, but by making it about T's. Okay. Any changes so far? Here? No? Nope. All right. Well, you're not adding integers anymore. You're adding elements of type T. Right? You are creating tree nodes of type T. Right? Tree nodes of type T, right? No changes there except for T, there you go, and T, there. Fix those. Uh-oh, that's the first real thing that we have to change now. We'll come back to that after we fixed everything else. T and T, there we go. Again, we have that problem, that's a misspelling. Now you won't complain about it. All right, now my in-order traversal is perfect. The only problem are these two lines because X is no longer an integer and the item is no longer an integer necessarily. So can we use strictly less than here to compare two things, stuff? No. What do we need instead? Something generic, something like a comparator. A comparator for what? Integers? No. A comparator for elements of type T. Right. And I'll just call this CMP for short. Why? What is it? What is it? It's a comparator, but is it ascending? Is it descending? Is it for integers? I don't know. It's for elements of type T. I don't care. All right. Oh, question on Piazza was, how do I get that thing in there? Well, how did I get the root in there? How did I get the size in there? I put it in the constructor. This .cmp is equal to, and of course you're now going to have to pass it in to the constructor. I have no problem making that final, right? Because are you suddenly going to change? You built your entire tree. Oh no, now I want to reverse it. No, create a new tree and do that. Right? I'll go ahead and make that final. And this root null CMP, there we go. Now I've got my comparator. How do I change the story here? I've got X and I've got the item. If they're in this order, I want to do that. If they're in that order on line 35, then I want to do that. How do I ask the comparator that question? This.cmp. What are you comparing again? X and, what was it? I erased it. Let me put it up here in a comment. So there we go. X is less than parent if this.cmp.compare. What are you comparing? You're comparing X and the parent's item. Now that's going to return something negative, positive, or 0, depending on the relative ordering of that. And hopefully I drove that home in Computer Science 1 and earlier in the semester too, because that is a pattern in literally every single damn programming language that there is. It's always, it's in every language, period. Why? Because you don't want to have to program 50 different functions for the same thing. You want generic programming. Generic programming existed before object-oriented programming in C, right? I don't want to have to write a sorting function for integers, a sorting function for doubles, a sorting function for ... right? And then anytime I introduce a new type, I need to write another sorting algorithm for it. You write one sorting algorithm and you use this pattern, negative, positive, or 0, right? So in this case, they're in order. What would I be expecting? Something negative, right? Just the opposite, what would I be expecting here? Positive. Right? And then, of course, I could check for 0 here, but that would be superfluous. All right? Same thing here. If X is less than the current item, if X is greater than the current item, so greater than, traverse right. And now all is right with, oh, not parent. Well, what is it? What was I comparing before? Current. There we go. Copy pasta, don't do that. There we go. Now, let's see if it works. Of course, I have to change it over here. If you have a parameterized class, you have to actually parameterize it. Because if I did it for strings, can I add integers down below? Nope. So I will parameterize it for integers so that I can add 20, 30, and 10. And then what do I need to do? I need to give it the comparator. So how do we build a comparator? Here's the old school way. Comparator for integers, CMP, is equal to new comparator. And I will create it and define it inline. This is an anonymous inline class declaration. I have to, of course, import it, java.util, implement the compare method here, and it takes 2 integers here. I prefer using A and B. O1 and O2 are just auto-generated code. Right? How do you compare 2 integers? Everything built into Java is already comparable. So I use the compare2 method. There we go. And I can pass off CMP. There we go. Nice. Run this. Hello? Oh, okay. Hello? I set my breakpoint here. Now let's, how are we going to test it? How did I propose that we test this? Using the Inorder traversal here, right? System.out.println. BST dot Inorder traversal. Now, if this is correct, if everything is correct, including my in-order traversal and my adding all of these methods and stuff like that, then what should I be? What should it look like? 10, 20, and 30. Hey, awesome. That feels good. How could I further test this and somewhat automate it? Random R. I like the idea of random variables, right? Is equal to new random, seeded with the current time, and then for int I equals 0, I is less than, say, 100, I plus plus, bst.add r.next int, and we'll bound it so that we don't have very large numbers so that we can actually look at them. At most 100. In fact, it'll go from 0 to 99. And then at the end, I'll go ahead and go with an in-order traversal here. Right. So let's keep it small. Only add 10 elements. But if this is correct, they should all be in order. Hey. Run it again and again and again and again and again. Set up your JUnit tests. Oh, wait. Why was it 5 or something? Oh, I know why it was 5. Right? It's not always going to be 10. Why? 1, 2, 3, 4, 5, 6. 4 things are missing? What if 2 of those things were 65? What would our add method have done? Nothing. No op. That was our choice, right? So, I can't believe that 4 items duplicated there, but whatever. There's 9 items, so at least one of them duplicated, right? You could go on to 235 discrete math and calculate the probability that any random number between 0 and 99, 0, 1, and 100, the probability of getting duplicates might be, I don't know, 5, 10% or something like that. But they all are order. That's all I really care about there, right? If we increase the size here, the probability that we're going to get duplicates there is now extremely low, right? But they're all still in order. And if we add 10,000 things, right? Oops. Parent, ooh, oh, good. I'm glad we broke it. What's going on? I know. So, the probability that we had duplicates here was very, very high. Let's go over here. Insert 20. What should happen? Nothing, right? No op. But I think that we're getting a bug here when the thing that we're trying to insert is, because this is going to be current and previous is up here. No. I don't see why we should be getting this bug, but we are getting this bug somehow. That the previous, or what was it, the current was null? Get item because parent is null. Yeah, the parent is going to be null, right? Parent is null. Okay. So where is that happening? Right here. Parent dot get item. So X compared to the parent. Parent would be the find parent. It found the root, and therefore the root parent of the root is going to be null, and that's why we have null right here. So yeah, I think that's why we're having a problem there. Right? So let's redesign this. In fact, let's not redesign it fully, but let's add another method here. In fact, I did the add method first on purpose because I wanted to get stuff in the tree. What's the first method that we talked about over here, though? The find, right? Now, are you going to find an index here? Does that make any sense? Find the index at which it exists? No. So are you going to find the tree node at which it exists? You could, but are you going to expose that to the outside world? Probably not. So let's go ahead and let's design that first of all. Public tree node. Right. We'll make it private. Sorry, private tree node of elements of type T. Find. tx. There we go. And it's going to be essentially find parent, but instead of finding the parent, what am I going to find? The current, right? So I don't even need previous, right? While that's not find, I can return current. There we go. And I don't need previous at all. And I'm not going to return the parent, I'm going to return the current. If you find what you're looking for, then return the current node. And that's the tree node right there. Is that it? Yeah. No, I want null here, right? Why do I want null there? If you find it, return it. If you don't find it, because you got out of it, then you'll return null. I guess that I could have left it as current. Why? How did we get out of that while loop? Current is null, so just go ahead and return it. There we go. All right, now that's private. Let's go ahead and make this into a public method. Public contain Boolean contains element of type x, or the element x. How do we do that? This dot find x is not equal to null, and return that. Because if you found the tree node containing x, then it contains x. If it is equal to null, then false, you did not contain the value x. That's what I exposed to the outside world here. Now, over in my add method here, what I can do is I can have another check, right? So if the root is null, then obviously we want to add it no matter what. Else if, now I can make a contains method here, right? If this dot contains x, then I will simply return, right? No op. That takes care of this corner case down here. And in fact, I now really want to redo this because I've got repeated code here to find the parent, repeated code here. I'd probably want to integrate those and have only one chunk of that code. I'll leave that as an exercise for you, though. All right. Now, if I fix this, then that shouldn't come. Now, it was random, of course, before. I can go ahead and try to increase the probability that it'll happen again by increasing the number of elements that I put into this tree. There we go. There we go. There we go. I'm satisfied that 5, 10, 15, 20, however many runs it takes here, I'm not going to hit that problem again. In fact, I can increase the probability even more by having lots and lots and lots of duplicates. Right? Looks like I fixed it. Right? Now, that's not rigorous testing. That's still ad hoc testing. What you would want to do is what we do in Lab 15, where we pre-designed. Where's my testing stuff? Binary search tree tests, right? What we did is we added a bunch of elements and then asked, well, were they successfully added by calling your find element method, get number of leaves, pre-order traversal test, in-order traversal test, post-order traversal test. I guess we didn't. Oh, I know what we did is we inserted them in such a way that we would know the structure and what it looks like, and then be able to verify the parent-child relationship. Right? This one right here. This is a large tree, and all we're doing is, it should be a balanced tree because we started with median element, and then we inserted all the things on the left side, all the things on the right side, in such an order to guarantee that it was a nice, well-formed tree that was full. Right? All right, that was our test, so. What else do we want to do on this? Oh, let's test that contains method. I don't know. We're basically testing all the methods here by randomizing this. I'm satisfied with that. Make sure it still works. Yep, good. All right, go up to 1,000 maybe. What else do we need to do? What can we do on this binary search tree? BST dot. I can add stuff. I can ask whether or not it contains binary search tree, right? I can ask, or I can do an in-order traversal to get all the elements, right? There's one other piece of the missing puzzle here. Right? And by the way, what if I want to input something else in there besides an integer? What if I wanted to put a student object in there? Instead, I would need a comparator for students. Now, is it going to hold them by their first name, or last name, first name, NUID, Or maybe if I wanted to put accounts in there, right? Is it going to hold it by its total value in ascending or descending order, right? It all depends on the comparator and how you implemented it. Right? But it doesn't matter, right? It doesn't matter if they're integers, whatever, comparator. It only matters that you have a comparator to say what the order is. Okay. All right, so what is the piece of the missing puzzle here? You can put stuff in. You can retrieve stuff. Remove stuff. You can update stuff too, right? CRUD, create, retrieve, update, and destroy. But update is just simply finding what you're looking for, pulling it out, deleting it. So find, retrieve, R, delete, and then insert the new element that you want. Right? So what do we need? I want a delete or remove. Say, I don't know, 40. After I've added it, bst.add 40. Then we'll go ahead and add in 10 random elements, and then we'll print it out, see that 40 is in there, remove 40, and see that 40 was removed. Okay. Now, obviously, this won't work yet because we haven't implemented this. That's not what I want. Let's go ahead and go over here. What did I call it? Remove or delete? Okay. Public void remove tx. There we go. And then return. Now, this will run, but of course it won't be correct because 40 will still be in there. There it is. Right. Why so small? Let's put in 500 instead. Something right in the middle. Right, there we go. 500 is still in there even after we've deleted it. So now let's implement that thing. First, we're going to have to whiteboard our idea for it. Okay. Some corner cases first. What if you wanted to remove 13? Does it exist? Nope. So there's a corner case, no op, right? It does not exist. We can immediately take care of that. If this dot contains, if it doesn't contain it, then what should we do? Nothing. Just return. Right. Okay. Done. All right. Let's remove 12. Step 1. What do we do? Find it. Right? How do we find it? That's why we implemented that thing, right? Find, and then you've got this tree node right here. Okay? Now, how do we delete it? Just need to sever this connection right here, right? So what would that involve? 12 is referring to its parent. What should we set that to? Strictly speaking, we don't need to, but we could. Null. More importantly, what do we set 15's left child to? Null. That will sever that connection and effectively get rid of 12. Okay. That's a good first case, right? Then to set parents left or right child, whichever the case may be, to null. Okay? So that's a to-do, right? I'll put a checkbox there, and then we'll check it later when we're done. What about remove 60? So, again, what's the first step? Find it. All right, done. How do I remove it? '50's right child to 60's right child, in this case. And then what else do we need to do? 90's parent should be now 50. Bypassing 60 and getting rid of it. We could, of course, set 60's parent to null and its right child to null. I'm not even going to worry about that, though, because this is Java. It's now eligible for garbage collection. The garbage collector will take care of it. Don't worry about it. Right. Okay. That'll work, right? So find it. Set to references. Dot, dot, dot. Okay. The next case. What if I wanted to remove 50? Well, again, step one, find it, right? I could clear it out. That would leave a gap, right? And maybe I could take this entire tree and promote it up here. Right? That'll work in this case, but it won't work in general when I've got something hanging off of this, right? What could I have hanging off of this that would make sense? 55. Right? Now can I do what I just proposed and move this thing up to be the new root? Nope. Why? Because 60 would be the new root, and it would have 40, 55, and 90 as children. Does that sound like a binary tree to you? Nope. All right. Back to the drawing board. I still like the idea of clearing it out. But structurally, I can't move things around. The children have to stay where they are. The parents have to stay where they are. What could I put into that gap, though, to preserve the binary tree property, that everything over here is going to be less, everything over here is going to be greater? What is a candidate from over here? Among all of these elements, which one could I throw up there and still have a binary search tree? Which one? 40, what? 49. Why 49? Right, well, let's put 49 up there and ask ourselves, is that still a binary search tree? Right, well, if 49 is gone, right? Suppose it's gone. Is everything over here less than 49? Yeah. Is everything over here greater than 49? Yeah. Okay. But 49 has a child. Can we just get rid of it? Yeah, we know how to do that. We did it with 60. It has one child. How do I do that? Just by bypassing it. Okay. What's another option here? I asked you about candidates over here. What about candidates over here? What could among these, what could I throw up here and have it preserve the binary search tree property? 60. Yeah, that's 60. It's a fat 60, but it is. Right? That means that I would have to get rid of 60. Do we know how to do that? Yeah, that was one example. Okay, so review. What is it about 49 and 60 that make those two things special? 49 is the max value in the left tree, and 60 is the max value, or not max, what is it? Min value in the right tree. Okay, well that worked out well for this particular example because we could bypass that, we knew how to do that. We could also bypass it here, we knew how to do that. But what happens when we've got, say, a tree that looks more like this? Right. Here's the max value in the left subtree. Right? So dot, 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 dot. Came down here. Here's the max value. But suppose that it has two children, A and B. Now we're back at square one, right? Is that the max value? No, why? Because it has a right child, right? By the binary search tree property, what do we have? That max is greater than B, or that B is greater than max, therefore this is not the maximum. If you have a maximum value, are you going to have a right child? Nope. And just the same argument, but mirror image. What about the minimum value? Are you going to have a left child? No. Right? So we've stumbled up onto something here. You want to delete this node. First of all, if it doesn't exist, you're done. Right? Otherwise, if it has no children, just delete it. If it has one child, change around some of its parameters. If it has two children, that's okay. Find the max or the min, and then promote that up, and now you can delete that one right there because you're guaranteed that it only has at most one child, and you know how to take care of those situations. Okay. We do not have enough time to do that, but we do have enough time to say, find the min or find the max. Right? In fact, I'll make this. Let's make it private first. Right? Tree node t get min tree node t node. I'll call it u. Right? There we go. So what I want to do here is I want to give you a tree node u, and I want you to find the minimum of that tree rooted at that node. Right. So finds the node containing the minimum because we're not allowing duplicates. So, and we don't have to say minimal. If there are if 5 was the minimum and there were two 5s with the multiple values of 5s, then we'd have to say minimal. But we're not allowing duplicates, so minimum. Finds the node containing the minimum value of the tree rooted at u. ... All right. So help me out. Let's whiteboard this. Let's start with a fresh picture. BST. There we go. Let's just do it for the root element here. Right? The entire tree. How do you find the minimum? Start at the node and go where? Left, 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 left until it has no children. It has no left child. Right? How do you find the maximum? Right, 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 right until you have no right child. That's the dumbest loop that you can write. Right? So let's go ahead and create a tree node, t current, and I'll start it at u. Right? But I wanted to make this more general. I didn't just want to find the minimum of the entire tree. I wanted to find the minimum of any subtree as well. So starting at u, I will go while current dot has left child. Right? Keep going left. Current is equal to current dot get left child. Right? When it has no left child, right, you are at the minimum. Return this, or not this, current dot get item. Oh no, sorry, just current, because we are returning the tree node here. There we go. What would the max look like? Start at u. While it has no right child, then go to the right child. ... Right? So all we need to do is find the minimum, check to see does it have a left child or a right child or neither, and then one of those three cases will tell us which one of these things we need to do. I leave that as in your capable hands, because on Thursday we're going to look at another type of tree. Right? Let's just make sure it works really quick though, right? Remove. So, to do, finish this on your own. This will be checked into the repo, but otherwise, let's make sure that it works. This dot minimum, or what is it? Minimum get min. There we go. Of say, I don't know, this dot root, and let's go ahead and system dot out dot println this dot get min this dot root. There we go. So what was the minimum of the tree that we built? Oh, I guess it's random, so we're going to have to examine it, right? The minimum was 486. Oh. We have to print the item, get item, not just the node. Now let's make sure it works. There we go. 77, 43, 72, 109. Consistently giving you the minimum every single time. Right? You could do that recursively too, although I wouldn't do it. It's just a dumb while loop, right? All right. Any questions? No questions online. Okay. Go ahead and play around with it. We are not continue working on assignment 7 due this Friday. Assignment 8 due next Friday along with your design document. So we recommend that you work in parallel on those because assignment 8 is all written and we have covered, I'd say maybe about at least 50% of the stuff necessary for that assignment, if not more. All right, see you on Thursday.